All right, now let's look at problem 15. So problem 15 says, let's say, suppose now it's 8 a.m. and then what time will it be after 2020 hours? Okay, so we know like each day has, every day has 24 hours. So 24 is like a cycle, right? 8 a.m. 24 is 8 a.m. again, 8 a.m. again. So this is basically asking what is the remainder when 2020 is divided by 24, right? Okay, so we start from here. So this is 8 a.m. And then after 24 hours, it's another 8 a.m., right? So 24, 24. So we have multiple 24 until in total here we have 2020 hours. Okay, so what we find is basically the remainder. So here the question is basically what is the remainder of 2020 when it is divided by 24, right? Okay, let's calculate this. So 2020 divided by 24, right? Okay, so this is 8. So it's 1892 and this 0, right? So it's 100. Okay, so we have 6, then we have 6. No, 4, sorry, we have 4. Oops. Well, 4 times this is 96. And then you see the remainder is 4. Okay, so we get the remainder is 4. Now the remainder is 4, that means after those, and this is the quotient, right? Quotient after 84. So finally, right here. So after those cycles of 24 in total, we have 84 cycles. Okay, so here we have a remainder is 4. So the remainder is 4. Okay, so we have 4. All right, so that means this cutoff is again it's 8 a.m. because you have those complete cycles of 24 hours, and then you add 4 extra hours. That's the remainder. So it's 8 plus 4, which is 12. Right? So that is 12 p.m. So this problem, as I said, is basically a find way to ask what the remainder of 2020 when it's divided by 24. Right? Okay. Number 16. So here, what we need to figure out. Okay, so here we have 2 cubes, and each cube has 6 numbers on it. Well, the problem says that every two numbers on 2 opposite faces, if you add them up, the sum is 15. And then we need to find the sum of numbers on those 7 faces that are hidden in the following picture. Okay, so here obviously you see we have 5 visible faces, and then we have the remaining 7 faces. They are hidden. Okay, all right. So what we do is let's separate them. Right? Let's separate these 2 cubes. Okay. All right. So this one is 3, and this is 4, and this is 5, and this is 2, and this is 1. Okay. All right. So then we can figure out for this one, because add up is it's 15, right? So this one will be 12, and this will be 10, and the one that is on the very back, so that one will be 11. Okay, so that's what we have. Right. So for this will be 13. So the one on the back, this will be 14. Right. Okay. So there are 2 faces which we don't know. So this is a question mark. This is a question mark. Okay. All right. So then we have the total sum is the 7 ones. Right. So let's add them up. 10 plus 11 plus 12 plus 14 plus 13 and plus these 2 numbers which are represented by question marks. Now here the point is for the 2 question marks, although we don't know they are, but they are opposite. So they are on the opposite faces, right? Opposite. Right. So this is opposite. Okay. So which means if you add them up, it's 15. Right? So that's what the problem says. Okay. So then let's calculate this. This one I have 33, and here we have 27, right? So 23 plus 27, and then plus 15. So you add them up is 75. Right? 75. Okay. All right. Now let's look at problem number 17. So number 17 says if an integer is called 30 special, if when it's divided by 13, the quotient and the remainder, they are the same. Okay? So then we need to figure out like how many 13 special integers that we have between 1 and 100. Right? So for example, let's look at one example. So the first 13 special integer is 14, because if I look at the 14, so 14 is 13 multiplied by 1 and a plus 1, right? So they are the same. So this one, this is the remainder. And this one is the quotient, right? Or I can write in the way like 13, 14, so this is 1, 13 is 1, right? Remainder and quotient. So you see, so this is the first example that when it's divided by 13, it has the same quotient and the remainder. Then obviously by the pattern, okay, what's the second one? No, the second one is shall be equals to, oops. So the second one will be 13 times 2 plus 2. And the third one is 13 times 3 plus 3. That's because the remainder and quotient are the same, right? So this is the quotient. Maybe let me rewrite like that. So this is the quotient. And here is the remainder. Right? So the next one will be 13 times 2 plus 2, 13 times 3 plus 3, and then 13 times 4 and plus 4, right? Okay, now we don't want this to go beyond 100. So the last one will be 13 times 7 plus 7. Now, of course, if you only care about this 13 special, you will keep going to 8 times 8 and plus 8, and all the way to 13 times 12 plus 12, because remainder has to be less than the 13, right? Okay, so this is the quotient part, right? And here is the remainder part, they are the same. All right, but here, because we require the numbers is no greater than 100, so we have cut off right here. So this is the number. Okay. So those are between, this is between 1 and 100, right? So in total, you see we have 7 such kind of numbers. So the answer is 7. Is 7. All right. So for this problem, basically, well, what you need to know is what is the quotient and what is the remainder, right? All right. Okay. Number 18. So here we have a 3-dimensional figure. We need to figure out the number of small cubes. Well, based on the picture, we have 2 ways to do. Number 1 is we just count directly, right? So we have 2 methods. Method 1, I say direct calculate. Okay, so if you look at the first layer, so let's calculate now first layer. So the first layer is no block is missing. So the first layer is obviously 4 times 4. Now let's look at the second layer. Second layer, you see 1 is missing, so it's 4 times 4 minus 1. And the third layer, 4 is missing, so 4 times 4 minus 4. And the fourth layer, the top layer, so it's 4 times 4 minus 9. Okay, so those are the number of cubes on each layer. Okay. All right, so then we have the total equals to 4 times 4. Maybe I put it, so this is the first floor. This is the second floor. This is the third floor. This is the fourth floor, right? Okay, all right, so then total is this one plus 4 times 4 minus 1 and plus 4 times 4 minus 4 and plus 4 times 4 minus 9, right? Okay, so we calculate 16 plus 16 minus 1 plus 16 minus 4 plus 16 minus 9. So this is 64 put together, and you minus 14, which is 50. If with this, we just go with the direct method. We directly calculate the number of blocks on each layer. Okay. All right, so now we can also do indirect method. Method 1. Method 2, indirect. Indirect is okay. So let's say this is a full cube. Nothing is missing. So then if the total, if 4, which we know, of course, is 4 times 4 times 4, which is 64. All right. So then we just need to calculate those missing parts. So those missing blocks, the number of missing blocks small cubes equals to. So here you're missing 1. And this you miss 4, and this layer you miss 9. Okay, so it's 1 plus 4 plus, plus 9, right? So that which is 14. Okay, so therefore, the total will be, so the number equals to the total 44 minus those missing ones, 14, which is 50, right? We just get the same answer. All right. Number 19. There are seven cards on the table. Okay, so 7 cards, 1, 2, 3, 4, 5, 6, 7. All right, so 3 people, Austin, Sam, and Stephanie. So each takes 2 cards. Okay, so for Austin said, okay, for his 2 cards, if they add up, equals to 7. And for Sam, so what Sam said is, all right, so for my 2 cards, the difference is 1. And then for Stephanie, that okay, so if I multiply them together, it's equals to 12, right? So those are numbers from 1 to 7. Now we need to figure out what is the one that is left behind, right? So what is the number on the card that is left and no one took it? Okay. All right. So what you do is we'll start from Stephanie because here the information is more useful than the previous 2. It says the multiplication of 12. We know if you look at numbers from 1 to 7, there's only 2 possibilities. One is 3 times 4, the other one is 2 times 6, right? Right, so we have 2 cases. Either is 2 times 6 is 12, or 3 times 4 is 12. So let's do case work. So case 1. So case 1, 1, 2, 3, 4, 5, 6, 7. Stephanie is 3, is 2 and 6. Is 2 and 6. Okay, so then we can get rid of 1, 2. Okay, so that means Austin and Sam will be choose from, they will choose cards from 1, 3, 4, 5, 7, right? 1, 3, 4, 5, 7. And then Austin says his number add up is 7, but add up to 7, for Austin, it has to be, if you add up to 7, we must have 3 plus 4, right? But then if you look at what is left, 1, 5, and 7, you cannot pick 2 such that to go for Sam, because for Sam is the difference has to be 1. So this is impossible. Get okay. So this is impossible, right? So then we say okay. Now let's look at the case 2. The case 2 Stephanie is 3 and 4. All right. So then we have 1, 2, 3, 4, 5, 6, 7. So 3 and 4 are gone. So for Austin and Sam, they can only choose, so let me put it here. So it's 1, 2, 5, 6, 7. All right. Okay, so then again, you look at different scenarios because for Austin, you have to add up to 7, right? So you have to add up to 7. For add up to 7, either you have 2 and 5, so that's one case, or you can do 1, 6, another case. Now, but for if you do 1, 6, what left is 2, 5, 7. And then you cannot find the 2, such that the difference is 1. So that is impossible. So again, this is impossible. Okay, so the only valid case is 2 and 5. But if it's 2 and 5, that means Austin has to be 2 and 5. Now, if it's 2 and 5, what Sam has to be 6 and 7. So 6 and 7. So based on all those information we combine together, we get the right distribution of costs between among these 3 people. So the conclusion is what is left behind. The left behind is 1. So, okay, so let's recall. So for Austin, so this is 3 plus 4, so 3, 4. For Sam is 7 minus 6, and for Stephanie, oh, okay, wait. So for Austin is 5 plus 2 equals to 7. For Sam is 7 minus 6 equals to 1. And for Stephanie is 2 is 3 times 4 equals to 12, right? So that's the distribution of costs. So what is left behind is the 1. 1. All right. Okay, so number 20. So number 20 here, we have 4 chairs, and we need to accommodate 2 couples that have 4 people around, okay, so around this table. Each one occupies a chair, and the requirement is each couple, the husband and the wife, they have to sit next to each other. Okay, so let's say we have 2 couples. So I can denote that this is a couple. That's the first couple, right? And the second couple is BB, right? Okay. All right. So now here we have 4 positions: 1, 2, 3, 4, right? Okay. Because so what we do is step 1. Okay. So step 1, let's accommodate the first couple. The couple AA, right? Or because they have to sit next to each other, so there are 4 ways, right? So there are 4 ways. Either we can do this. So we have 1, 2, 1, 2, 2. All right. Okay, so that's what we have. So we can do is this is this position to occupy these two, this 2, or this 2, right? Okay, so we have A, we have A, we have A, we have A, right? All right, and then the other 2 positions are for the second couple, right? So BB, and this is for BB. This is also for BB, and this is for BB, right? All right. So now, because each one you can switch, right? Because husband and wife, they can switch position. So I have 2 ways to occupy, and this is 2 ways. So you multiply together, you have 4 ways for each one. So this is the multiplication principle, right? So remember, what is the multiplication principle? Multiplication says if I have different steps to accomplish a mission, if each step has different number of the number of different ways, then the total number of ways you just do the multiplication. So like for this, I have 2 ways to completely settle the first couple, right? The critical switch. Again, I have 2 ways to completely settle the second couple. So to completely settle the 2 couples, these are 2 steps. Right? Just take the multiplication. The 2 times 2 is 4, right? Equals 4. All right. So similarly, so here's also 4. This 4. This 4. So the total, right? So the total is 4 times 4, which is 16, right? Which is 16. Okay, so here we do not consider, sometimes you see problems that says, oh, if you rotate the table and then we consider they are the same after rotation, just like if you try to color like a cube, or you try to color, if you try to use different beads to form a necklace, you can do rotation and you can do flip, and it's still the same. But here we exclude those so-called symmetry issues. Like we say, okay, they all represent different arrangements for this problem. Okay, so that's why we have 60. Right? We have 60. We consider consider all different scenarios. So that's what we have 60. Okay. All right. Okay. That's it. Have a nice weekend.